You guys have learned over the past number of years that you have certain operations that you do in mathematics, and you have certain groups. And this is really kind of the basis for our algebra. And when you take an algebra theory course in the future, you'll look at this even deeper. But what are some operations that, again, you've learned over the years? Right, so we'll just start with those, okay? When you started adding, did you start adding irrational numbers? No, you started adding things like you had certain groups, like whole numbers. And then you advanced on to, at some point, integers using positive and negative. And then there came to a point where you said you're going to use all real numbers. And actually, in another class, you've actually added and subtracted matrices or multiplied them as well. Well, there's another piece here, and that's what about a different group? What about a group of functions? You know, how do these operations work out with that kind of a group? And in fact, we even added um, a new operation. Does anybody remember what that operation was that we added on Friday? Starts with a C. Composition. So we had composition was our other operation. That's what we did on Friday. So if you missed that, you want to watch a video, go from there. So the certain properties, these operations, and how they affect these different groups is something that you continue to look at throughout all of algebra. In fact, in this next lesson tomorrow, we're going to learn about another operation. It's called function inverse operation. And so, you know, operations are not limited to these, and our groups are not limited to simply all real numbers. Understand that? Because I didn't understand it really until I got to be about a sophomore in college taking an abstract algebra course. And something I always just taken for granted was that we always work with all real numbers and these are operations. No, it does change. Love it when that happens. So here we go. We start with our notes. And the first part here is pretty easy. If you want to do function addition, you can simply do f of x and add it to g of x. And if you want to do function subtraction, f of x minus g of x. Multiplication, f of x times g of x. And division, f of x divided by g of x. So these are our operations. It was different than composition was different though. We learned that on Friday. But if you want to combine two functions together using addition, you simply add them together. The domain is what's interesting. The domain is going to be the intersection of the domain of G and the domain of F. So that's intersection, the overlap of the two domains. And it's the same way for addition and subtraction and multiplication and division, except we need to exclude for g of x is equal to 0. Can somebody tell me why we exclude where g of x is equal to 0? Yes. Because you would get 0 in the denominator, and that creates an undefined value, which we don't know. So what I want to do is I just want to list f plus g, f minus g, f times g, and f divided by g, and I want to list their domains. So f plus g of x is equal to, I simply add the two together, and I get x squared plus x minus 1. Simple enough, right? And if we subtract, we distribute the subtraction sign through g of x, we get x squared minus x plus 1. And if we multiply them, we'll distribute the x squared through, and we get x to the third minus x squared. And if we divide them, we get x squared over x minus 1. There's really nothing I can do to simplify that. Just write it as follows. Now the domain is a little bit more interesting. I've taught this as many ways as I can. I don't know what more to say other than just continue to come back to it. But you do know what the graph of x squared looks like, right? And we've identified domains by looking at the graphs and by just looking at the actual equation. You know what the domain of x squared is? Meaning all real numbers. There's nothing that you can't plug in there. Okay? So you can plug in any number in the real number set, you're going to get an output. How about x minus 1? What graph does that make? Line shifted down 1, its domain would be all real numbers. So the overlap between all real numbers and all real numbers is all real numbers, or from negative infinity to positive infinity. Now, we can write that if it's that case for addition, it will be for subtraction and multiplication. But division is different. We have to look where g of x is equal to 0. Where is x minus 1 equal to 0? At an x value of 1. So therefore, we would say x not equal to 1, or you could write from negative infinity to 1, union with 1 to infinity. And you can tell, obviously, just by looking at it at this point as well. Right? Okay. B. A little bit different. We have some square root pieces there. So I'm going to list f plus g of x. If I have two square roots, say square root of 3 plus square root of 5, can I just add those together? Square root of 8? Nope. The radicand has to be the same. If the radicand is not the same, you can't combine it. If you had 2 roots of 3 plus 5 roots of 3, then yeah, that's 7 roots of 3. But that's how you got to write it. What up, dog? Just checking some answers. Oh, for what we did today? Okay, there you go. It's right there. Yep, that's what you want to look at. Okay, so we cannot combine these together. All we can write is 2 minus x plus the square root of x squared minus 9. So that's all we can write, okay? And for subtraction, it would be the same way. F minus g of x. Square root of 2 minus x minus the square root of x squared minus 9. We'll list the domain over there in a second. Can you multiply two radicals together? Yes, you are allowed to multiply them. And so you have f times g of x. And we're going to multiply this all out. So 2 times x squared is 2x squared. 2 times negative 9, negative 18. Negative x times x squared is negative x to the third. And negative x times negative 9 is plus 9x. And if I divide two radicals, if I have a radical on the top and a radical on bottom, I can simply write it as square root of the whole thing, right? So I will do that for division. F divided by g of x is equal to the square root of 2 minus x over x squared minus 9. Now, to everybody who says you can't have a radical in the denominator, you can as long as as long as there's a variable involved. So if it was, say, just the square root of 7 in the denominator, then you would have to rationalize the denominator, but we don't have to in this case. Okay, so now we need to consider the domains, and then we'll be done. These domains are a little bit trickier, and I'm going to need some scratch space to work. So the square root of 2 minus x, the square root of x squared minus 9. How do I find the domains of these two functions? Greater than or equal to 0. I cannot take the square root of a negative number, so I force the inside to be positive. That is not a quadratic. It's a linear, so I can just solve it like you normally would. Minus 2, negative x is greater than or equal to negative 2. X is less than or equal to positive 2. So from negative infinity to positive 2, is your domain for that one. Now, if you don't like solving it algebraically, go ahead. Look at the look at the graph. You guys know what the graph looks like. It's shifted over the right 2 units, and it goes that way. That's from negative infinity to 2. How do you know that stuff? It's like, how do you know the factors of 14 or 2 and 7? You got good at it after a while, right? Same type of thing. You got to get better at finding domains and looking at them. How about this one? What I have to do here? How do I solve that inequality? Okay, factor. Then what? Yeah, you got two options. You either make a graph or you make a chart. If it's not linear, you have to make a chart or graph it. Now, I know what the graph looks like because we're really good at graphing in this class. So a -3 and +3, and it goes up because it's positive. See, we've just taught about quadratics. You guys know all that stuff. So where is it positive? Right? Here's a question for you. What if it was, instead of x squared minus 9, what if it was x squared plus 3? What does that graph look like? Shifted up how many units? What's the domain of that? Where's that? Yeah, that's above the x-axis all the time, right? So if you have the square root of x squared plus 3, that domain is all real numbers. I challenge you to find a number to plug in for x that you can't eventually take square root of. You won't come up with one. What if I had this? That shifted down how many units? And does it go up or down? Where is that greater than or equal to 0? It's not. It's never greater than or equal to 0. There's not a single number that you can plug in to make that work. You try all you want. I promise you won't find one. You will not find one. Okay? So let's look at our two combined here. We need to look at the overlap. We have from negative infinity to 2. So our first domain is from negative infinity to 2, right? And our second domain is from negative infinity to -3, union with 3 to infinity. The question is, where do the two graphs overlap? And that is their domain. It's where the intersection is. Do they overlap here? Do they overlap here? Do they overlap here? Do they overlap here? Yes, they overlap everywhere here, okay? From negative infinity to -3. That will be their intersection. Oops, don't do that. So let's go back to our chart and we'll write it like it matters. The domain from negative infinity to -3. If I found it for addition, I found it for subtraction and multiplication and almost division. Is there a number in this set such that if you plugged it in, you get 0 in the denominator? What number? So therefore, we have to exclude -3 from our solution set. You know, it has to be the overlap of the two domains. And so if you look back at the graph that we made, you can see that the green one, x less than or equal to 2, it overlaps only with this red part. So that's why we keep this domain. So, and we don't include the 3 to infinity either. We don't include that. We don't include from -3 to 2. We only include the overlap from here on over, which is that. Okay. So, um, the first one was obviously letter A was pretty straightforward. Letter B is a little bit more challenging. Today you just have 5 problems to work on for the rest of the hour. Tomorrow's gonna be a lot of notes, and you'll get your study guide. Page 225, numbers 1 through 5.